Okay, so you got the Orion caps. I've been calling it Artemis because it's part of the Artemis mission. I've been calling it ART and using ART. Okay, I don't want to use an abbreviation of Orion because O looks too much like a zero and it could be confused with a zero. It could also be confused with one of the planets. Okay. So anyhow, we start off with what we already know at 1 over x, okay, and 1 over x squared. I'm doing this with the intermediate algebra course now because I want to give them a little bit of stuff that'll help them get started in precalculus, okay? So this is all familiar, okay? And you've got these graphs, okay? And this graph has a little different shape than this. Goes down a little faster, levels off a little faster, okay? Now the point is, what this graph tells you is basically how much energy, which translates to how much fuel you need to boost that rocket out to the moon, okay? Or to boost it from the ground up. But mainly the latter. Okay, so that's how much energy you're going to need. If you're here at, let's say, 1 Earth radius, which is like pretty much in low Earth orbit, okay? And you want to get out to 2 Earth radii, then the amount of fuel you need is basically this minus this, okay? Which is this much from the graph. So you need this much fuel, okay? Now this graph keeps going, and of course it gets really flat, okay? Approaches the x-axis with an asymptote. So if you want to get out to 3 Earth radii, well, the amount of fuel you need is down to where 1/3 is here, okay? So you need this much fuel. If you want to go to 4 Earth radii, well, you need 1/16 as much, or 1/4 as much, okay? And so forth. And to boost the rocket so far that it never comes back, you need at least this much. Okay, because that gives it enough energy. Well, this thing never touches the x-axis. That gives us enough energy to go forever, assuming it doesn't run into anything. Okay. This curve comes from 1 over x function, can be interpreted very easily. Let's say that this is how much force you have at half an Earth diameter, which is an Earth radius, okay? It's that diameter there is about 8,000 miles, the radius is about 4,000. So this is how much force you feel if you're on the surface of the Earth, like what you're feeling right now, okay? What you would really feel if you fell 6 feet. That force would accelerate you, you'd hit the ground pretty hard. But you're young and healthy, unlike me, I'd probably break. I'm pretty healthy, but I'm not that young anymore. You know, tendons, ligaments get stiffer and stuff like that. I think I'd do a 6-foot fall without getting hurt, but I'm not going to test it. Okay. It's 12 feet is about as far as even a trained athlete can fall and avoid injury. You can luck out if you hit right and avoid injury. The chances are you're at least going to badly sprain an ankle or something, or worse. And if you fall from too high, like 100 feet, you hit so hard that when your head snaps down and fractures your thoracic spine and you're dead. Now, if it doesn't, you have so many internal injuries, you're going to die. Okay, well, that's what gravity does. So you don't want to mess with it. And of course, we've got an instinctual avoidance, instinctually avoid falling from high places. All animals do. All big animals do. Little animals don't so much. Okay, because there's a saying, I'm digressing, but there's a saying that if you throw a man down a well, he dies. If a horse falls down a well, he splatters. Throw a rat down a well, he just climbs back up and goes on with his life. Okay, it's because of surface to, of mass to surface area ratio. Okay, and that's all a power function. So, you know, understand power functions, understand proportionalities. It's not hard to conclude those things. Okay, if you scale me up to 7 feet, I'll weigh probably about 280 pounds. Scrawny guy that I am, I'll still go up to 280 pounds if you add a foot to my height and everything else grows proportional. Okay, so I'll be almost twice as high, twice as massive. Okay, but I'll only be maybe 50% strong. Okay, so if I can do pull-ups now, I probably can't do it at 280 pounds. If you scale me up to 280 pounds. So 280 pounder who can do pull-ups is impressive. Guy my size who can do pull-ups, well, that's what you expect. If, you know, unless you're confident. And then my age, I don't know if I can do pull-up because my shoulders are messed up. Used to be able to do a bunch of them. No desire to test it. Okay. That's all related to what you're learning in precalculus. You're learning the skills to analyze those sorts of things. Okay, so anyhow, if you go out twice as far, we should be another 4,000 miles. So we're 4,000 miles from the center of the Earth. If we got 8,000 miles, that'd be like going from here to here. And the force gravity exerts on you goes all the way from this down to this. 1/4 as much. And then if you go out to 4 times the Earth's radius, you're down to 1/4 of that. Well, you take that account when you're putting a rocket in orbit. So it's all pretty cool. There's a bunch of stuff here you don't need to see. I'm looking for. Oh. Okay, so this just says what I just said. Okay, that the inverse of square graph for positive x, for negative x, that it's not relevant to this discussion. So for this model of gravitational force of the Earth and the spacecraft, that only works if you're going away from the Earth. Positive values of r. R is your distance from the center of the Earth. F is the gravitational force. Right there's your curve, but we relabel it. Instead of 2 here, we put 24,000. Okay, be 24,000 kilometers. Instead of 4 up here, we put 2,000 pounds of force. And then the graph scales, so you can tell if you know how far you are in kilometers from the center of the Earth. And these are approximate. That should actually be 6,348 or something like that. Depends on where you are in the Earth. But I'm just rounding it off to 6,000. These are pretty accurate. Okay, for a spacecraft that weighs 2,000 pounds on Earth. Okay, and you can tell they're 20,000 pounds. Okay, this curve tells you the force the spacecraft feels relative to the Earth. Now, Also, spacecraft gets in the vicinity of the moon. Moon's got a lot less mass than the Earth. Doesn't pull as hard. So this purple curve is just another reciprocal square curve. And that tells you how much force you experience at a given distance from the center of the moon. It's not actually a really good curve. You get the idea. Shouldn't be that close to it. Yeah, actually it does. Actually it works. So all that's relevant because what happens is that spacecraft is in orbit around the Earth, then you kick it up to an orbit around the moon. Okay. Now, our distance from the center of the Earth is 4,000 miles, and the moon is about 240,000 miles. Okay, so you put it on scale. If Earth is this big, the moon's out there pretty far. So you put the spacecraft in orbit, and it goes out here, and it goes into an elliptical orbit. Now, how many of you have to take precalculus 2? Anybody? Good. You need to take it? Nope. 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 Okay, so I won't talk that much about ellipses. I will in precalculus class, because some of the people I think are going to need to take it. But you get that in precalculus 2. Precalculus 2 is tough. Pretty tough course. This is precalculus 1's a tough enough course. Precalculus 2 is at least a letter grade harder, maybe 2. Although if you do well in precalculus 1, precalculus 2 is not bad. This one talks about kinetic energy, which is just how much energy you need to get there. When you burn the rocket, you make it go faster and increase its kinetic energy. And then it coasts, but it keeps losing energy because Earth keeps pulling it back. Okay, just like you're trying to coast uphill. Gravity of the Earth makes it harder to do that. Okay, that's an analogy from physics. You don't need to really know. Now, a lot of this other stuff is just physics-related stuff. But you see that these two curves that we started the course with almost the first day have real-life applications because it's a multi-billion-dollar project here. Also, there's speculation that we plan to put people on the moon within about 3 years. They've been there before, no matter what the conspiracy theories tell you, they've been there. Conspiracy theories give you a simplistic answer that's very appealing, doesn't make you think. That's what conspiracy theories do. And conspiracy theories on the right and the left, okay? Everybody's susceptible to conspiracy theories, and there are plenty of idiots out there that want you to believe them. So you got to watch that. That is ultimately, and within your lifetime, probably before you hit middle age, it's going to have economic repercussions. It's going to support the economy. Depending on a lot of other factors, should make everybody richer. And by the time you're my age, you might have been there a couple of times, okay, if you're inclined. I would have been inclined when I was younger, but now I've seen everything, so. Okay, and people my age can do it. It's not that stressful, not that strenuous. I put John Glenn in orbit. He's the first guy to orbit the Earth, the first American to orbit the Earth. Really, really impressive guy. He went to the Senate, then he retired from the Senate in his late 70s, and they sent him up to orbit. He had no problem with it. They grounded him because of an inner ear thing that wasn't really necessary. But that's just a story stuff. Add a little color to the explanation. Right here is the expression for gravitational force. You can ignore this part of it. This is just a power function. You multiply 1 over r squared, which is 1 over x squared, by big G, big M, and little m. Big M's the mass of the Earth, little m's the mass of you or satellite or whatever. R is how far you are from the center of the Earth. And big G, everybody knows big G, right? 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. Everybody knows that. You learned it in elementary school. You probably haven't used it that much. You do manage to climb hills and get around and throw things without having to do these calculations. I think it's pathetic, but that's just the way it is. Okay. Okay, there it is. Those are connections with precalculus. It goes on. You see some of the calculations that we end up doing. I never really did write down all the details of this calculation because I did this in physics class where everybody knew that if you begin the lemma of R squared thing. We take that to calculate the force exerted by the moon, that purple curve, and the force exerted by the Earth, that other curve, at different distances. Right now, well, the spacecraft got to within, well, it got to within like 80 miles of the surface of the moon, okay, yesterday. It's really neat that NASA listened to me and delayed all this stuff so that we were doing gravitation in physics class. And at a point in my intermediate algebra class, we talked about all this stuff, okay? So, that pass to the moon happened yesterday. The thing was launched 6 days ago. This tells you the ratio of the force exerted by the moon to the force exerted by the Earth. Okay. Now, when you're like 80 miles from the surface of the moon, you're like just a little over 1,000 miles from the center of the moon. And the force exerted by the moon is 1,000 times the force exerted by the Earth. Okay. Actually, I could calculate it. Let's see. You're at 240 here. You're at 1 here. If you square 240, you get 60-some thousand. You divide that by 80, you get 800. Yeah, that's pretty close. About 1,000 times stronger. This allows you to easily calculate it. You just take this thing and square it. It's just another squaring function. Okay. And then you can use some arrows and stuff to indicate the force you have to the moon, the force you have toward the Earth, put it together and get that force and all that stuff. And I couldn't even attempt to explain that because it's well beyond the scope of what we can do. But we're using the kind of calculations in all of this. Number one that you do in this course. Now you enhance that with a little bit of calculus. You got to do some integrals. Okay. And you can do a pretty good job of understanding how this whole thing works. It's very complicated, but you cut through the complication. Now, NASA actually goes to Lagrangian mechanics and all that stuff, okay? That stuff gets really hard, really complicated, okay? I can't do what NASA does. Now, if I don't study that in depth, I could do most of what NASA does, but those guys are all smarter than I am. Okay. Okay. Well, there's one. Let's go ahead and do precalculus. Okay, you have this an island with 1,000 people, not a certain kind of people. You're immortal. They don't reproduce. Makes them mortal kind of long teeth. But anyhow, 500 of those people are sane. The rest are demented. So every month, %10 of the same become demented. You can imagine, you got a bunch of sane and demented people, they kind of have influence on each other, okay? Turns out on this island, that sanity is a stronger influence than dementedness, okay? So that %20 of the demented, that's going to be hard to read. %20 of the demented become sane. Now, in your homework, you dealt with transition matrices. It's a transition matrix for this. And transition matrices are one of the more important things that we deal with at this stage. Because you have transition matrices, I forget what all the examples were, but for example, the stock market. You say that, okay, there's a 10% chance that the market's going to be up tomorrow, 5% chance it's going to be down, and an 85% chance it's not going to change much. Okay, you have transitions in the probabilities that govern the market, which might influence how you invest your money or how some professional that you employ pay a little bit to chooses to invest your money, like if you got a retirement account. So it'll be very relevant, and that's just one example. There are all kinds of examples where we take the probabilities of different transitions and make important decisions. Okay. And as you know, if you've done the homework, you represent that as a matrix. Now I'm going to build that out of this model. So first question I'm going to ask you to work out. After 1 month, how many sane and how many demented people are you going to have? It'll give you a hint here. No, actually, I'm going to see what you do. My guess is that some of you are going to need a hint because of how to calculate this. But think about it for a minute. And then when I see everybody growing frustrated and ready to string me up, I'll give you a hint to relieve your stress. Actually, as you're getting started, I'm going to give you just a little bit of a hint. Take what you've got here and calculate whatever you can. Okay? Because once you calculate something, it's probably, in this case, going to have a meaning that helps you get to the solution. Don't sit there and think, oh, how am I going to find that? Sit there and do what you can, and then look at where you're trying to go again and see if what you calculated can help you get there. If this thing doesn't start working without a delay. Okay. So, well, everybody did calculations equivalent to what I'm going to do here. I'm going to do it in a little different manner. Some people actually use the transition matrix, but I'm not going to introduce that just yet. Just going to say, okay, here you got $500 sane and $500 demented. You know that 10% of the sane become demented. So I can kind of put that in a schematic. Okay, so we got 10% is 50. Everybody got that, so I don't have to explain how we got 50. 10% of 500 is 50, right? So this many sane go over to the demented camp. Okay. And 20% of 500 is 100, so 100 of these come over here. So the net change is, well, you got 500 minus 50 plus 100 here now. Okay. You lose the 50, you gain the 100. And here you got 500 plus 50 minus 100 because one way the 50 here decreases the number of sane, which is, well, it's negative here, but it increases the number of demented. So what any of these numbers do to one, they do the opposite to the other side. Okay. So that's 550. This is 450. Now the same thing happens again. Okay, the 10% of these go over, which is 55, and 20% of these come over here. It's easy to calculate. 10% of 550, everybody can see is 55, and 20% of 450 is 90. That's calculate that in your head, but if not, yeah, use the calculator if you need to. Try to use your head. So that we have 500 minus 55 plus 90, which is 585. And over here, we have 500 minus 55 plus 55 minus 90, which is 415. Okay, and this keeps going. So you can do this and this, and then we come down here and do it again and keep on doing it. So that's not hard. You could set up a spreadsheet in Excel to do this easily. If you know Excel, you know how to do spreadsheet, which I assume that most people either do or will do when they take the IT course, information technology course. I believe that's covered in the course. Another way to do it is if S is a number sane, D is a number demented, then what you have is 0.1 S. Make sure we see that as an S, not a 5. Still looks a lot like a 5. I'm going to make an S. We'll put a little loop in it. Okay. matrix is. Then we have 0.2D. Now, after the transition then, we have the number same minus 0.1 times the number same plus 0.2 times the number demented over here in the same category. In that, in the demented category, we have the number demented plus 0.1 times the number same minus 0.2 times the number of demented, right? That makes sense? Because, just in this example, what's 0.1 times your number of sane here? 0.1 times 500, of course, 0.1 is 10%. That's 50. So you're losing those 50. So that's your minus 0.1s. And then a plus 0.2d. You're gaining the 100 from your demented. Then over here, you're gaining the 0.1s that you lost over here. And you're losing the 0.2d that you gained over here. Not particularly difficult to understand because everybody worked this out correctly in the first iteration, okay? Okay, well, now I'm going to make a definition. Let me do one more. I can simplify this expression. Okay. Can you write this expression? Can you simplify this expression? And can you simplify this expression? So I'm going to give you a minute to see if you can do that. You've got some like terms in each expression. You can combine like terms. Okay, to simplify this, pretty clear if that's 8x plus 5y, right? Because you could factor the x out, you have 10 minus 2 quantity times x. So 10 minus 2 is 8. Of course, you know from habit that you can combine like terms in this manner, but it comes down to factoring. And you kind of maybe want to remember that to make sure that you're doing it right. It's not something you're likely to make a mistake. Okay, so what's x minus 0.1x? Well, that's 1x minus 0.1x. That gives us 0.9x. And this is, you got y minus a 0.2y. You have a, we'll do a 0.1x plus 0.8y. I'll just put this in parentheses because it's easier to see, especially since a lot of you are still reading my S's as 5s. Sometimes and not others, okay? You won't do that if you go back to what I wrote here and understand that this represents S, this represents minus 0.1S, and this represents 0.2D, right? So let's just kind of, okay, so this is S. Minus 0.1S plus 0.2G. And this is D, because the 500 over here is your demented. Plus 0.1S minus 0.2D. Okay. Again, the only thing might be confusing is why did I use S for 500? Why did I use D for 500 over here? because over here, I'm calculating based on the number of sane. S is 500. D is also 500. So this is S. Over here, this is D. If I'd have started with different numbers, well, the calculations would have been more complicated the first few transitions. So I wanted to start with the same number. But there could be a little confusion about why this is D and why this is S right there. Hopefully we overcome that. Okay, well, this is obvious. Well, then, if you read this as an S and this is an S, okay, and this is an S, you see I've got S minus 0.1 S, and this gives me 0.9 S. Plus 0.2 D. This gives me, I'm going to do S first, it's going to give me 0.1 S plus 0.8 D. Sorry, I'm having to write these a little bigger than I did them. Running out of space. Okay. That makes sense. This applies to any transition. So now we have our new number of S and our new number of D. We just apply the same rule. We take 90% of the same, because what's 0.9 S mean? It means 90% of the same. If 10% of the same become demented, that leaves you 90% of the same who are still sane. That's all that means. Okay. And 20% of the demented is the number of demented that becomes sane. Just like over here, your 0.1 S is the number of sane that become demented. That's easy to understand. And the 80% of your demented who are still demented. 20% of your demented have become sane, so only 80% of the demented people stay that way. But of course, the demented crowd picks up 10% of the same. All right, now, a little notation. Use matrix practice, because now we're going to get into the matrix. This is I'm going to call it a row vector, and this is a column vector. Okay. When we multiply a row by a column, the rule is very simple. We multiply the first number in the row by the first number in the column, and we multiply the second number in the row by the second number in the column. Match up the first numbers, match up the second numbers, and add those products. So this is 0.9 S plus 0.2 D. So this is just another way of representing this calculation. Okay, so actually all of this comes into the calculation, but if we do the calculation in this actually shorthand notation, where we understand what we mean when we multiply a row by a column, here's what we get. Now I'll just observe right now that you got to multiply each number in the row by its corresponding number in the column. So you've got to have as many numbers in the column as you have in the row, or you don't have anything to match up. If you had 3 numbers in the column, there'd be no number to multiply by that third, and the whole thing would become meaningless. So if I had SDB and 0.9, 0.2, there'd be nothing to multiply by the B, and it wouldn't work. It's not defined. It's not a mathematical operation. Okay. Mathematical operation, row times column. The row has to have the same length as the column. So you always have a number to match up with each number and even. Okay. So write down the matrix or the matrix product that would correspond to 0.1s plus 0.8d. What row and column, when you multiply, would give you 0.1s plus 0.8d? Okay, everybody did quite well. That's a little confusing. First of all, you got to make sure you understand what we're trying to do here. We're trying to get this. Okay. So we want to get this. So make it colorful. Then I'll try to find myself a path. Snake around here. So to get 0.1s plus 0.8d, we're going to imitate what we did here. The same way that this calculation gives us this, we want a calculation that will give us this. Okay. Now, there are a couple of ways this could actually be written out. But we want to keep the SD order intact. Okay. We don't want to always be making a decision about which one comes first here. So it's always going to be SD. Then what numbers do we need? Well, at this stage, when it's phrased like this, everybody saw that this would be 0.1 and this would be 0.8. One times S plus 0.8 times D. So that this matches this. Okay. Now we can put all these calculations into a single matrix product. It's not difficult to understand. There's a calculation. Okay. Well, if we multiply the first row by SD, as we see now, we're going to get .9s plus 0.2d. Since this is the first row multiplied by this, we're going to put it in the first row of a new column matrix. Okay. So just organizing these calculations in a way that involves matrix multiplication. And matrix multiplication is something any software program, Excel, even Excel, it's a little harder to set up in Excel, but it's not hard to get used to. Okay. Or in the real computer algebra systems, you just type this in. Now, the way you type in a matrix, well, I'm not going to go into that. It's easy. Not difficult to see at all. Okay, so you get this. Now, the second row times this column, well, we just saw that this row times this gives us this. So this times this is going to give us 0.1s plus 0.8d. Okay. And that's matrix multiplication. If you understand that, the rest of matrix multiplication is easy. And really all you have to do is understand what it means to multiply a row by a column. First number times first number, second number times second number, and add them up. Okay. And then again, the convention, if you got several rows, then I could have more rows there, it wouldn't match the Sane-Demented model, but in another model, I might have more rows here. It might not be S and D, it might just be X and Y, whatever. Then I'd have, if I've got 4 rows in this matrix, now each row still has to match up with the column, okay? So I'd have 4 rows, each with 2 numbers. And then I'd end up with 4 rows in this column. That's all there is to it. It's a simple mechanical procedure. Okay, well, then I can apply this matrix twice. Okay. Meaning I could take this matrix and multiply by itself, square the matrix, and I get this. If I want to see what my number sane and demented is after 20 years, I just take the 20th power of this matrix and multiply by my sane and demented numbers. Now, I'd like to go into more detail on that, but again, with time and so forth. If you understand this, then you understand these transition matrices and how they can be used. And the point is that once you have your transition matrix, you can make a prediction as far into the future as you want. Now, whether that prediction is valid 50 years into the future when everything has changed and all the conditions have changed, all the conditions that made the model valid for the next few years might not stay valid for the next 50 years. It might be real good for the next few years, okay? And those are the ways mathematics is used in any number of fields, including business, finance, science, all over the place, okay? The most successful scientific theory of all is quantum mechanics. Now, y'all, yeah, you did some quantum mechanics, Hamiltonian matrices and stuff like that in elementary school, right? No, that's a whole new subject. There's a linear algebra course. In the linear algebra course we teach gets you up to the point where you can understand what those things are, whether you can actually apply them to the way matter behaves at the microscopic level, submicroscopic level, at the atomic level, molecular level. I can't do it. Just because it takes at least a couple of years to get to where you can really deal with that stuff of intense graduate level study. Okay. I didn't have time, and maybe I'm not even smart enough to have done it because you got to be pretty smart to do it. Real smart. Okay, the whole point is that matrices are all over the place. Okay. You use matrices to do computer graphics. Okay. Use matrices to condense pictures with billions of pixels into a code with 10,000. Okay. Pieces of information. And big deal. Okay. Which is why we're including it in this course. I'll also say that the community college system statewide doesn't require that we communicate this, And I get the word communicate, to include this in the course. We're including it at a pretty easy level. Okay, we're not going into a whole linear algebra course, but we're including it because we know how important it is. And whoever made the decision to statewide level had their reasons. They're articulating with four-year schools and stuff like that. So you got to leave something out. Yeah. We're not leaving it out. Then all the full-time math faculty here agree on this. And our dual enrollment adjuncts agree on it. They know how important it is. So I'm not slamming Virginia Community Colleges, and they got a pretty good syllabus. They say you can include it if you want to. And we choose to include it. For your benefit, even though you might be suffering a little bit right now. Not much suffering, it's not that hard. Yeah, and Sue's getting worse and worse about responding to the record button. It's hard to keep straight. You press it, nothing happens. You think, well, I didn't hit it right. You press it again, and then it does what you don't want it to do. There's a matrix operation that we can use to model that. I'm not going to get into that again. Okay. This development is the clearest development I've been able to devise. Tells you what a transition matrix is and why it works. Now, there are also 3x3 transition matrices. Okay. If we have sane, demented, and borderline people, okay, now borderline's a serious psychiatric diagnosis, whereas demented really isn't. We just kind of know when we see it. And I don't know, some of you have a little bit of it. Yeah, I don't know about that look. Okay. You look sane. Very good. And I'm glad to see you today. Okay. Then we'd have 3 transitions. Okay, sane to demented, sane to borderline, demented to sane. Okay, so we'd have 3 rows and 3 columns. Now you'd have S, D, B. We have to have numbers to multiply those. Well, you see that in the assignment. And there are some 3-dimensional transition matrices there. They don't ask you to do a lot of multiplication by the things, but they ask you to set them up. And once you've set them up, once you've got the matrix, you can calculate any power of it and predict as far into the future as you think the model would be valid. With just a couple of keystrokes. Using computer algebra system, there's nobody in their right mind that doesn't know about eigenvalues and eigenvectors is going to be able to calculate powers of this matrix. Okay, and you don't want to know about eigenvalues and eigenvectors unless you know a lot more mathematics. It gets fairly challenging at a much higher level. Okay, again, that's why we do this.